Bismillahirrahmanirrahim. So in the last lecture we discussed about the dislocations, why they are formed within the material, and why they are critical to the deformation systems. So the thing is, whenever a material deforms, it is going to deform when the atoms move from one place to the other. This is how the material deforms. So atoms do not move randomly in any direction when the force is applied. Rather it will move only in the energetically favorable directions. Energetically favorable as in the direction which it will be easiest for the atoms to move. They're going to move in that direction at the low stress. So if the atom has a possibility to move in a direction in which there is less force is required, it is going to deform and it is going to move in that particular direction. Those directions are defined by Miller indices within a crystal structure. And the easiest direction in which that material can move, that is called close packed directions or highest density directions. As we have seen in the crystal structures, the directions in which the atoms are in contact with each other, those directions have highest density of atoms. So whenever a material deforms, the atoms will move in the direction in which the material so the atoms will move in a direction in which they are in contact with each other. So that's why the defining various directions at the atomic level is important, because we need to know in which direction the atoms will move when the material is deformed. Okay, and then there will be specific planes on which the atoms move from one place to the other. So then next thing is the atoms when they are moving within a crystal structure, when is a crystal during deformation. The thing is, usually it's not the single atom which moves from one place to another. Rather it's a series of atoms, a line of atoms which move from one place to the other, and these lines of atoms are called dislocations. So these lines of atoms which are called dislocations, they tend to move together in a coordinated way from one place to the other, or in a particular direction under the influence of the force. Okay, so the length of the atom, the length of the dislocation will be like similar to the will be smaller than, of course, the grain of atoms or the crystal of atoms, but they usually tend to move in a coordinated way. The dislocations tend to form within a material because during the dislocation, and that is simply a misarrangement of not misarrangement, you can say it is the extra half plane which can be formed within a system during the solidification process, or they may also form during the deformation of the material. So as you can see here, there is an extra half plane of atoms which are coming from any which comes up till here, and then there is here it is discontinued. So this line of atoms is an extra line of atoms which theoretically shouldn't be there, but practically there is. That's why this is called a defect. So this is easier to move when the force is applied, so that's why this defect will move in the either way under the influence of the force, and this is how this coordinated layer of atoms will move. When the atoms move, the material tends to deform. Okay, so dislocations look like these black lines within a system, within a material. And this is an actual image or the picture of the dislocations, how they look in within a crystal. Okay, so this is the TEM micrograph like we discussed earlier, and here is the extra half plane. This is the actual atoms which can be observed within the and the TEM micrographs, transmission electron microscopy. This microscopy gives the micrographs in which it is possible to locate the position of the atom. These dots represents the atoms within a material. Okay, so the thing is, as we discussed, the atoms will move in a particular direction on a particular planes, and these things depends upon the crystal structure of the material. For example, magnesium has the hexagonal closed packed HCP structure, and the HCP structure has only one plane and three directions in which the material can move, in which the atoms can move. So when this particular material is deformed, it is difficult for the atoms to move, so that's why this material will behave in a brittle way. So there will be less deformation, ये material ज़्यादा deform नहीं होगा, and it will tend to deform. Not much, and then it will break after a little deformation. So इस मटेरियल को ज़्यादा डिफॉर्म नहीं किया जा सकता प्लास्टिकली, ठीक है। इस मटेरियल को ज़्यादा डिफॉर्मेशन पॉसिबल नहीं है, इसे बेंड नहीं कर सकते, इसे रोलिंग नहीं कर सकते, इसकी ये डिफॉर्म हो जाएगा, ब्रेक हो जाएगा, ठीक है। ऑन कंट्रेरी एल्यूमिनियम विच हैज़ FCC स्ट्रक्चर, this has a lot of closed pack planes and directions, or the high density planes and directions, so this can be deformed easily, and it can be deformed to many % of the material. So it's more like if this material is rolled, or if this material is extruded, it is easier for this material to deform or roll or extrude, but this material cannot be deformed much. So इसकी deformation ज़्यादा possible है, इसकी deformation ज़्यादा नहीं हो सकती, and this thing depends upon the crystal structure. Now I will show you a couple of videos of how the dislocation move within a material. Okay.
Now look at an edge dislocation. This is a commonly used model of a lattice called simple cubic. Using this simplified lattice, we can understand the basic principle of an edge dislocation. When a shearing force is applied to the lattice, a plane will try to find a new plane to bond with in order to relieve the tensions in the lattice. The plane that has been released will then be without a bond. The line this occurs along is called the dislocation line or edge. If the dislocation continues, the dislocation will eventually leak out into the grain boundary. In a real lattice, the planes and directions are not as easy to identify as in a simple cubic lattice, but the principles are the same. We will now show you an edge dislocation in an FCC lattice. This is how local HCP form in the FCC lattice, and is the principle of how deformation in metal occurs.
So here in this video you can see these lines are the dislocations actually. So this is a very controlled experiment in which the stress is applied in this direction. Okay. So and this is these lines are actually the dislocations, and the movement of these lines represent the movement of atoms or the movement of dislocation. And so here the dislocation is moving in this direction and in a coordinated way, because here in this experiment the force is applied only in this direction in a very controlled way. Okay. So here this is the so here you can see the dislocations are going in that direction because the force is applied in that direction, so the atoms are moving in that direction. So dislocations are moving in that direction. Okay. So this is how the material deforms in the at the atomic level. Okay. But the thing is the actual material in the actual material the dislocation cannot move in the straight line, and this is because of the reason that the stresses are not applied in the same direction to all the grains or all the atoms within a material, because as we discussed before, the crystals within a unit cell, there are the crystals within a material, there can be thousands or the millions of crystals within a material, within like simply an iron bar which we commonly use. So all these crystals or all these grains are randomly oriented. So within one unit cell, within one crystal, the atoms may be when the tensile stresses are applied in one particular direction, the you can say when the force is applied in the tensile direction, there may be some crystals which are oriented favorably, so so they will tend to deform first, and the atoms can move easily in particular direction which is easiest for them to move. But for the crystal which is not arranged favorably, which has a different orientation, so in that for that particular case, the force which will act on the atoms for them to move, they can only move in a particular direction, but that direction, if that is not aligned with the tensile forces direction, then the atoms still will move in the direction which is favorable at the crystal level. So there will be a component of the force that work on those crystals, so they will move in a little bit different direction to deform the material overall. So thing is, when the atoms move within an actual system, then that sort of coordinated movement which saw in the last video, that thing is not observed usually. Rather, this kind of movement of the dislocation is observed more commonly in the materials. So as you can see here, this is a dislocation which is pinned within a system because of the different precipitates which are formed within a crystal. So when the force is continuously applied in this direction, so atoms tend to move in that direction. So this is the way that directions. This is the way how new dislocations are formed within a crystal structure. So like we discussed, the dislocation may form during solidification, and the new dislocation can form in this way. There are many ways in which the dislocation can form within a crystal system, within a material. One way is during dislocation, during solidification. The another way is during deformation. And this is an example how the dislocation may form during deformation. As you can see that the dislocation form here, and then when the stress level is increased, then the dislocation move from this direction to in this particular direction. These are the new dislocations which are being generated from this place. And here there are many dislocations which are pinned due to certain reason. So once again, this movement dislocation is hindered here. When the movement of dislocation is hindered, it means that deformation of the material is becoming difficult. So that's this is one way to increase the strength of the material to make it difficult for the dislocation to move. If the movement of dislocation is difficult, then the strength of the material is increased. Okay. Now we'll come back to this. We'll come back to the slides, and here there are various dislocations and crystal structure, various crystal structure as we discussed before. Now if we go next to the next type of defects, which is called 2D defects. Okay, so what are 2D defects? 2D defects are the surface of the grain boundaries, or surface of the crystal structure. When two crystals meet, they have irregularity at that meeting point, and that irregularity is called grain boundary. And that boundary has a irregular surface of atoms, and surfaces are two-dimensional. So those surfaces are an example of two-dimensional defects. Okay. So those defects form during the solidification of the material. Let's say material is first it is liquefied, it is melted at a higher temperature. Then when it is cooled, then the solidification occurs. How solidification occurs? It's not like the whole material is converted at a single at a single point. A whole material which is liquid is transformed into the solid form. It does not happen that way. Usually what happens at the atomic level, first there are tiny crystals, or the tiny nuclei which form of like few atoms which solidify or which form a crystal structure because of the solidification. Then those nuclei tend to grow, and how those nuclei grow? Then the atoms tends to attach to these nuclei, solid nuclei, and the liquid transforms into the solid part. So इसमें क्या होगा कि एक nuclei बनेंगे, solid nuclei, लिक्विड के अंदर, जिस तरह ये है, यहाँ पे सारा पोर्शन लिक्विड का है, इसमें टाइनी जो ये जो पॉइंट्स हैं ये एक्चुअली न्यूक्लियाई हैं, या आप कह लें टाइनी पार्टिकल्स जो हैं ये सॉलिड पार्टिकल्स हैं. दिस पार्टिकल्स टेंड टू फॉर्म बिकॉज ऑफ द व्हेन द टेम्परेचर इज डिक्रीज टू द फ्रीजिंग पॉइंट. सो फ्रीजिंग पॉइंट आ गया, ठीक है. फ्रीजिंग पॉइंट पे क्या होगा कि मटेरियल टेंड टू फ्रीज. इस तरह नहीं होगा सारे का सारा मटेरियल एकदम जो सॉलिडिफाई हो जाए. फर्स्ट देयर विल बी टाइनी क्रिस्टल्स और टाइनी न्यूक्लियाई फॉर्म विद इन अ लिक्विड, ठीक है. एंड देन दीज क्रिस्टल्स विल ग्रो. ग्रो किस पे करेंगे? एट द एक्सपेंस ऑफ दिस लिक्विड. दिस लिक्विड विल टेंड टू ट्रांसफॉर्म इनटू द सॉलिड फॉर्म. सॉलिड फॉर्म इसका नहीं होगा कि रैंडमली सॉलिडिफाई हो जाए. पहले कुछ क्रिस्टल्स फॉर्म, न्यूक्लियाई फॉर्म होंगी, देन दीज न्यूक्लियाई विल टेंड टू ग्रो एट द एक्सपेंस ऑफ दिस लिक्विड. सो लिक्विफाइड एटम्स जो हैं ये सॉलिडिफाइड एटम बनेंगे जब यहाँ पे इनके साथ अटैच होते जाएंगे. एंड दीज crystals will grow and eventually they will meet each other when this all this liquid is expensed. So what will form? They will tend to grow and then they will tend to have a boundary between each other. जिस तरह ये फॉर एग्जांपल क्रिस्टल है, ये ग्रो होगा तो यहाँ तक लेट से आ गया, ये क्रिस्टल ग्रो होकर यहाँ तक आ गया, ठीक है. तो कोई ना कोई एक ये समझ लेंगे एक बाउंड्री बनेगी. लेट से ये क्रिस्टल ग्रो हुआ, ग्रो होते होते तो यहाँ पे पहुँच गया, ठीक है. इस तरह ग्रो हो गया. लेट से ये जो है ये ग्रो होकर इस तरह ग्रो हो गया, ठीक है. लेट से तो यहाँ पे जो बाउंड्री बनेगी, दिस बाउंड्री इज कॉल्ड ग्रेन बाउंड्री और अ क्रिस्टल बाउंड्री. जो ग्रेन बाउंड्री जो है यहाँ पे एटम जो हैं वो ना इस क्रिस्टल कह सकते हैं इस क्रिस्टल से बिलोंग करते हैं, ना इस क्रिस्टल से बिलोंग करते हैं. सो दे आर मोर और लेस अ बिट random in nature. So randomized atoms are defects, so this is called a defect. यहाँ पे इस क्रिस्टल के में भी इस डायरेक्शन में एटम्स अरेंज्ड हो, यहाँ पे में भी इस डायरेक्शन में अरेंज्ड हो, ठीक है. तो यहाँ पे जो डायरेक्शनल मिसमैच है इसकी वजह से एटम जो है थोड़े से रैंडमली अरेंज्ड है. तो इसलिए इस बाउंड्री के ऊपर जो एटम्स उन्हें हम ग्रेन बाउंड्री एटम्स कहते हैं, ठीक है. एक क्रिस्टल को एक ग्रेन भी कहते हैं. सो इसे हम क्रिस्टल भी कह सकते हैं, ग्रेन भी कह सकते हैं. सो यहाँ पे जो मैच कर रहे हैं इस पॉइंट के ऊपर, इसे हम कहेंगे मिसमैच्ड आइटम्स आर ये कैन से ग्रेन बाउंड्री आइटम्स, ठीक है. सो ग्रेन बाउंड्री जो दे आर टाइप ऑफ ट्रू डिफेक्ट्स. यहाँ पे वही चीज़ हमें नज़र आ रही है, ठीक है, कि एटम जो हैं ये यहाँ पे बाउंड्री, यहाँ पे जो ग्रेन बाउंड्री लाइंस जो हैं ये एक्चुअली ग्रेन बाउंड्री लाइंस हैं, ठीक है. और ये ग्रेन बाउंड्री जो है डिफेक्ट है, सही है. सो इससे हम ये भी देख सकते हैं कि इस ग्रेन या इस क्रिस्टल का साइज इतना है, इस क्रिस्टल का साइज से ज़्यादा, इसका कम है. इन नेचर किसी सब क्रिस्टल का साइज सेम नहीं होता, किसी का कम है देखें, किसी का ज़्यादा है. अब उनकी जो शेप जो है ये पहले राउंड होते हैं जब यहाँ से ग्रो करना शुरू करते हैं. ऐसे जब से इन कॉन्टैक्ट आते हैं तो ये थोड़ी सी शेप इनकी रैंडम हो जाती है, ठीक है. सो दिस इज हाउ द एक्चुअल द मटेरियल कन्वर्ट्स फ्रॉम द लिक्विड स्टेट टू द सॉलिड स्टेट. इस तरह नहीं होता कि सारे का सारा मटेरियल खुद ब खुद इस तरह कन्वर्ट हो जाए. पहले यहाँ पर न्यूक्लियाई जनरेट होंगे, वो न्यूक्लियाई ग्रो करेंगे एंड देन दे विल फॉर्म द देन दे विल कम्प्लीटली सॉलिडिफाई. इस तरह का स्ट्रक्चर बनेगा, ठीक है. तो इसमें क्या है कि नेक्स्ट जिस तरह मैं बता रहा था कि ये ग्रेन बाउंड्री मिसमैच, जैसे यहाँ पे देख सकते हैं लेट्स से ये सेम क्रिस्टल स्ट्रक्चर है इन दोनों क्रिस्टल्स का, ठीक है. लेकिन इसमें एटम्स इस डायरेक्शन में अरेंज्ड हैं, ठीक है, सेम क्रिस्टल में. इसमें इस डायरेक्शन में अरेंज्ड है, ठीक है, ये आप देख सकते हैं. तो इसमें देखें ये एंगल है मिसमैच का ना इन दोनों के दरमियान. तो यहाँ पे जो एटम्स हैं थोड़े से, ये वाले एटम देखें ना ये रैंडमली थोड़े से अरेंज्ड है ना यहाँ पे. तो ये जो है ये ग्रेन बाउंड्री है, ठीक है. अब यहाँ पे देखें इन दोनों के दरमियान मिसमैच थोड़ा कम है, इस डायरेक्शन में है, ये इस डायरेक्शन में है, थोड़ा सा मिसमैच जो है कम है, यहाँ पे थोड़ा ज़्यादा है. इट डिपेंड्स, क्योंकि रैंडम ओरिएंटेशन है, किसी में मिसमैच थोड़ा ज़्यादा आ जाएगा, किसी में कम आ जाएगा. लेकिन ये देखिए बाउंड्री के ऊपर जो आइटम्स है वो रैंडम में थोड़े से अरेंज, इसलिए ये जो जगह ये डिफेक्ट है. यहाँ पे परफेक्ट क्रिस्टल है, यहाँ पे परफेक्ट क्रिस्टल है. सो दिस डिफेक्ट इज कॉल्ड ग्रेन बाउंड्री डिफेक्ट, ठीक है. और जो है दीज ग्रेन बाउंड्रीज यूजुअली हैव हाई मोबिलिटी एंड हाई डिफ्यूजिविटी. मोबिलिटी एंड डिफ्यूजिविटी किस चीज़ की? एटम्स की. जो यहाँ पे आप देख रहे हैं थोड़ी सी जगह एम्प्टी भी है तो यहाँ पे एटम मूवमेंट इजी है. और दूसरा यहाँ ये हाई एनर्जी पॉइंट्स हैं, हाई डिफेक्ट्स जो यूजुअली हाई एनर्जी पॉइंट्स होते हैं. तो ये जो डिफेक्ट है इसके अलोंग जो है डिफ्यूजन ईजी है क्योंकि ये हाई एनर्जी एरियाज है, ठीक है। सो दिस इज़ द एंड ऑफ दिस चैप्टर। ओके, थैंक यू, अल्लाह हाफिज़।